So I guess most of you are here. I can see like how many? 5 plus 13, around 18. So almost the class is full, I guess. Okay. And I assume you have received my email, otherwise you all won't have been here. Okay. So in our last class, what we did, we were talking about the classification of ODE in terms of this linearity, and then we were talking about different type of solutions. Okay, so those solutions that we were discussing, they were like your general solution. Of course, it comes from some parameter, family of curves. Okay, and then particular solution, and of course singular solution. Singular solution. Also, we are talking about the domain of definition of the solution, or simply interval of the solution. Okay, I hope I'm audible, right? So let us get back to our last example. As you can see in the slide, so we were you were told to verify that your y equal to your x to the power 16. So this is a solution of the differential equation, your dy dx. This is equal to x y to the power half. This can be easily verified. Okay, and then we have seen that, if I do something like so, along with this, these two also become the solution of the differential equation. And we had already discussed about what kind of solution is this. As you can see in the very first one here, in the not the very first one here, this one you can see that this represents a one parameter family of curves, because if we change the parameter, we get different solution curves, right? So all the solution curves together, it is going to represent a one parameter family of curves. And I also discussed about that depending upon the order of the differential equation, you are going to have either one parameter, two parameter, or if you have an ODE which is nth order, so then you are going to have an n parameter family of curves. Okay, and again, I was also discussing about your direction field. So what we are going to do, at some juncture, we are also going to talk about integral curves. Okay, please, remind me this if I forget it. So this I want to just mention about it a little bit when we will come to an initial problem, of course, which is be defined for a linear differential equation. Linear differential equation of first order. So we'll discuss about that later on. Okay, so now let us come to the today's. Okay, so you have already seen like these three type of solutions. And in those solutions, so you may assume that throughout the whole interval, you can define the solution. You can define the solution in a certain way, which is going to be valid throughout the whole interval. So now you please look at the slide. So here I have considered an example here. Just a minute, I missed somebody. So here, the differential equation that is being taken is your x diagram minus 4y equal to 0. Okay. So now, if you want to solve it, I mean, you can easily verify. That y equal to c x to the power 4 is also a solution. Fine. Is it also a solution? So what kind of solution is that? Can somebody tell me? Can somebody tell me? I mean, y equal to cx to the power 4, which I say that it is the solution of the given differential equation. So it represents what type of solution? Can somebody unmute and tell me?
So general solution.
Or I mean, it is a one parameter solution, right? So, like say, if I want to draw the graph of the solution, I mean, suppose this is x, this is y, and of course, this being a polynomial, it is going to be varied throughout the whole real line. So, this could be one of my interval of definition. So basically, this is going to be the maximal or the largest interval of definition of the solution, right? And I can take any subset of it, which also is going to constitute an interval of definition of the solution, right? So now this is going to be something like a if c is greater than 0, then I am going to have a curve like this, and if c is less than 0, then I'm going to get a curve like this, right? So you can see that simply by varying this parameter c, I can get solutions of I can get solution curves of different types. Okay. So now what happens if I consider this curve? If I consider this curve, is it also going to be a solution? Can someone tell me whether this is also going to be a solution in the whole real line, in the often interval negative infinity to positive infinity? Is it going to be a solution for this given differential equation? Yes?
Yes.
Right. It is definitely going to be a solution. But although this is a solution, you simply cannot express in terms of a single expression y equal to cx to the power 4, which is going to be varied throughout the whole interval. Okay? So in those cases, we may have to define this kind of solution piecewise. So that is what actually you see in the slides. Is it okay with everybody? Right? So here, this is what I was talking about. I mean, when c is greater than 0 and c is less than 0. And now this, as you can see, that what is being written there, that piecewise defined solution. So this is also a solution. So this is an interesting example. Okay, like say you may have a solution which is piecewise defined and which you may not be able to express in terms of a single expression like this, but still it can be a solution of a given differential equation. Right? Okay. So now let me come to some exercises here. So in my last class, I told you that I have already uploaded one write-up, not really write-up. It is a chapter from Stewart's Stewart's calculus book. And in the calculus book, there is a chapter. It is called How Derivatives Affect the Shape of a Graph. I hope you have already downloaded it. Have you already seen it? Anybody has already seen it? No?
Yes, sir, I have.
Okay, at least somebody has opened that PDF file. So how that is going to be useful? So right now, I'm just simply going to do a couple of examples here. Okay, so that particular chapter, it tells you about how you can interpret the first order and second order derivative of a function of a single variable. Okay, so it is going to tell you how you can interpret not only the graph of a single variable function, but also its first and second order derivative, the graphs of its first and second order derivative. So basically, just by looking at the graphs of the first and second order derivative, how you can like have some idea about that original solution. So this is what it talks about. Okay, so now you may have seen, what is the exercise here, and please look at your assignment sheets also. I have given many examples there. The more you work them out, so better your understanding is going to be. Okay. So here, see, as you can see, that it is given that y equal to 5x. So it is a solution of a given differential equation. So this is simply, I think it is a minus by. A minus by. Okay. The very first question is, by inspection, find two constant solutions of this equation. Can you find two constant solutions? So basically, you have to find out something like y equal to c1 and y equal to c2 in such a way that they are going to satisfy the given differential equation. That's it. Can somebody give me a way how to find it out?
So y is equal to 0 and y is equal to a by b.
Yeah, simply plug in the right side is
equal to 0.
Yeah, and the whatever whatever value of y comes out of it, it is going to constitute the solution. So basically, for A, what you do, simply plug in right hand side equal to 0. So that is going to give you y equal to 0 and y equal to your A by B, right? So definitely, if you plug those values on the right hand side, you can see that either of them is going to yield the right hand side as 0. And again, they being constant, again their first order derivative themselves are 0. So we have already verified that these two are solutions, and as you can see, they are constant. So that is what these are. Two constant solutions of this equation. Okay. So now the next question is, only using the differential equation, you have to find out the intervals on which the solution curve is. Firstly, I think it is increasing, and the interval on which the solution curve is going to be decreasing. Okay. So now, and that particular write-up that I have uploaded, how derivatives affect the shape of a curve. So over there, and probably you have already studied that, a function is function, say y is a function of x. So it is monotonically increasing in a certain interval. Okay. So if your y prime x is greater than or equal to 0, right? Fine. And if it is decreasing, if this is less than or equal to 0. Okay. Fine. So now let us have a look at the given differential equation. Okay. So I may be using the whole blackboard. So a minus bx. Okay. So now obviously your dy dx will be greater than 0 when both of them are greater than 0. Fine. Is it okay? Or when this happens. Okay. And remember, whatever comes out of this, you should be able to find a common intersection. Okay, which is going to constitute the interval on which both of them are going to be valid. if you cannot find a common intersection, then I mean we are going to simply discard that. Is it okay? So now if I look at my first option, then you can see that this is y greater than 0, and then from here it will, sorry, this is y. From here it is okay. So basically this I can write as simply this. Okay. So now let me tell you what I was meaning by that common intersection. See, suppose this is the y line. This is the y line, and of course we have been given that both a and b are positive. So this is 0. So suppose somewhere this is a by b. So the first one, it gives me what? Y greater than 0. So it gives me this part. Okay, and the second part, it gives me y greater than a by y less than a by b. So if I take their common intersection, it is simply going to give me this interval. Is it okay? Fine. Now, if you work with the second part, you again, I mean this is dy. You won't be able to find a common intersection there. Okay, fine. So what is going to happen here? So it is going to be increasing on this interval. It is going to be increasing on this interval. So what about decreasing? Can somebody tell me about this decreasing? In a similar way, you will see that it is decreasing on the interval y less than 0 and y greater than a by b. Is it okay? Fine. Now I'll come back to this. You don't need to worry about it, because once I do the D part, you will get answers to all this stuff. Okay. So this is basically interpreting the solution curve even without solving the given differential equation. This is what it is all about. Is it okay? Fine. So now the third part is using only the differential equation, explain y equal to a by 2b is the y coordinate or a point of inflection of the graph of the non-constant solution y equal to phi of x. And that is also very straightforward. So you know that a point of inflection is simply given by what? If a curve is given by y equal to f of phi of x, so how can you find out the point of inflection?
Double derivative is 0.
Double derivative is 0. And what is the geometrical interpretation of the point of inflection?
So the curve is going to
Increasing or decreasing?
on convex curve to concave curve, or concave to from concave to concave.
Okay. Fine. So the second one is correct. It goes from concave to convex or vice versa. Okay. So now what I'm going to do, I'm not going to use the words convex. I'm going to use the words concave upwards and concave downwards. Okay. So what I mean by that, let me tell you, like concave upwards is simply like this U. Okay. And concave downwards is like this. That's it. Because concave and convex, it confuses me. And many mathematics textbooks, they simply follow this notation. So this is upwards, and this one is downwards, concave downwards. Okay. So if it changes from this shape to this shape, or this shape to this shape, those particular points where it undergoes those kind of changes, we call them as inflection points. So here, so that is why, in order to find out the points of inflection, so what we have to do, we have to simply find out the second derivative of this. Okay. And from here, you can easily see that. You can easily see that once you, plug that in equal to 0, you will see that you are going to get a by 2b as the point of inflection. Okay. And you please work it out. And I have given some more examples like this in your assignment sheet. Please, work them out also. So let me come to the, last part. Let me come to the last part. So, just a minute. Right. This, yeah. So, basically, I have these two intervals, not really two intervals. This is, in fact, here I have got two disjoint intervals I have here. Okay, so it was increasing, and here it was decreasing. It was decreasing. Okay, so now suppose okay, suppose this is your, maybe I'll just push it down so that it is easier for me to draw. Okay, fine. Suppose this is 0, of course, this is y, so this is x, and okay. This is y equal to 0. This is y equal to a by b. This is a by b. So this point is something like a by 2b. Is it okay? Fine. And then what is happening? Of course, these two lines, this line and this line, they are the constant solutions. Fine. And then I have been given that when y is less than 0, so basically in this portion, and when y is greater than ab, this portion, what happens? The function is monotonically decreasing. So it must be from here, it must be something like this. Okay, and here it should be something like this. Okay, fine. And we have found out that in this interval, it is increasing. In this interval, from this interval, it is increasing, right? And of course, I have another information from the exercise, 7C, that y equal to a by a by 2b is a point of inflection. So over the point of inflection, it is going to change from concave upwards to downwards or vice versa. And again, it is also increasing. So like if it is increasing, so then what is going to happen? So it is going to be something like this. It is my let me try to draw it. See, suppose this is concave upwards and then this is concave downwards here. Okay, so the shape is going to be something like this. Is it okay with everybody? Any question? No? Okay. But anyway, I have given more examples there in your assignment sheet. Please go through it and you'll be fine. Don't worry about it. And the next, this is also pretty straightforward. In fact, I have already uploaded these lectures. So here I'll just tell you about the trick. How to find out the interval of definition when the solution is given as an explicit function. Okay. So what you have to do here? Here you can see that there are two curves. Okay. And in both the curves, you will see that somewhere, if you draw a vertical line, it is going to, intersect the curve at 2 points more than once. Is it okay? For example, here, this one, something like this. Here you can see that, I mean, if you draw some vertical line, right? So what you are going to get, corresponding to one value of x, you are going to get two values of y. Okay, fine. So we have to, I mean, separate out the curves in such a way that, I can define them. I can define them explicitly in a certain interval. Of course, here, what we are going to do, we are going to draw some vertical tangent to the curve. Okay, like say this one, and here, I mean, this y-axis is already a tangent. So obviously, you know that if I take the range of x from this point to this, right, it is going to give me some interval of definition. Fine? Is it okay? So then, what I can do, I can simply divide it. I can simply divide it into two parts, from where it is touching at one end and ending by touching the vertical tangent at the other end. So, right, if I divide the curve like this, so then I can define this as something like phi 1x and this as something like phi 2x, right? And they are going to give me two explicit solutions. Is it okay with everybody? Fine. So similarly, you can do with the next problem also. Probably over there, you have to segment the curve into more than two parts there. Okay. So I don't want to spend much time on that because I have already given you enough, assignments there. Okay. Please work them out. So now, what I'm going to do, I'm going to come to a specific family of curves. So you may have done it earlier. I mean, orthogonal trajectories. Okay, so can you tell me what is orthogonal trajectory? Yeah, somebody please unmute and tell me. Yes. Yeah, can anybody tell me? Probably now I get it. You during your BSc days, probably in BSc you studied it, right? Yes.
So orthogonal trajectory is a curve which cut the every member of the family orthogonally. Cut every orthogonally every member of the family of solutions. So,
can you give me an example?
For example,
Family of straight line and the subfamily of circle, they are orthogonal.
Okay, good. Yeah. See, you may be thinking why I am roping this in, because in your actual research, many a time, for example, I deal with computational fluid dynamics and more precisely like say fluid dynamics. So fluid dynamics, later on if you take it, we have an elective there. I mean, then you will see that the streamlines are orthogonal to equipotential lines. Okay, potential curves. So over there, this concept is going to act. Okay, and since this is a particular family of curves and we are already discussing a family of curves, I am going to discuss about it. And more so because I would like to tell you something from here. What you should do, say, rather than exactly following some kind of given expression or some kind of formula through which you can work out some example, I just want to give you the idea of finding orthogonal trajectory in polar coordinates, which is going to be very helpful. You will see that a very simple concept can lead you to finding solutions of certain problems in a much easier way. Okay, fine. So now let me come to orthogonal trajectory. So as somebody has already told me that if you consider, say, a particular family of curves, particular one parameter family of curve, and find another family of curve in such a way that they intersect each other orthogonally. So basically what happens, if you take one curve from one family, who are here, Sudip Kumar, Saidul Alam. Okay, if you take one curve from Kumar family and the other curve from Alam family, okay, then at their point of intersection, the tangents to the respective curves, they must be orthogonal to each other. Okay, so that is the definition of, orthogonality in such cases, and that is the definition of orthogonal trajectories. So if, like, say, Kumar family of curve, that is a particular trajectory, so its orthogonal trajectory will be depicted by Alam family of curves if they follow the property that at their points of intersection, the respective tangents are perpendicular to each other. That's it. Okay, fine. So now I'll come back to the circle thing. So now let me get back, because so far we have discussed many concepts about differential equation, but we haven't actually worked it out, because you have already done it, how to work it out. Like, say, how to construct a differential equation out of a given family of curve, right? But let us do some kind of revision. For that, let me consider firstly simply this one, x squared plus y squared equals c squared. You know that this is a circle of radius c centered at the origin. Fine. So now, if I want to find out the differential equation which represents this family of circles, then what I have to do, I have to differentiate it. I have to differentiate it with respect to the independent variable x, and then what I will have to do, I have to simply what? Then what I'll do? In order to find out the differential equation of this family of curve?
Into derivative, first order derivative.
Okay.
Then
Okay. Fine. So from here, okay, maybe what I do, then from here, dy dx equal to minus x by y. That's it, right? So from here, I'll get this as easy as that. Okay, then what about this? How to find out the differential equations? Then
putting the value of c in the main equation, family of circle equation.
okay, okay. Probably you tried to work it out that way. No, don't say putting the value of c. We are simply going to eliminate the parameter present in the family of curve. Okay, please think in that way. Fine. We are simply going to get rid of the parameter from these two equations. That's it. Is it okay? So then, if I do that, so if you divide, say, this a by b, so I'm going to get x squared plus x squared, 2x plus 2y dy dx. This is going to be equal to x, right? Yeah. So this will give me x squared plus y squared equal to 2x squared plus 2xy. You may be thinking, why am I doing all this stuff? I have a special intention. So basically, eventually what is going to happen? I mean, dy dx, this is going to be this y squared, and then this is going to be minus x squared divided by 2xy. Okay, see why I have wrote this in, because see, although we have studied all those stuff, so most of those stuff that we studied, I mean, that was, I'm sorry to say, in order to get some big flat inflated marks in our exam. But now let us try to understand the concept as clearly as possible. Okay, fine. So now, in the first case, when we consider the family of circles centered at the origin, you can see that like I said, we didn't have to do the elimination of C, right? Because it was already eliminated, isn't it? But in the second case, we couldn't eliminate it. Okay, fine. So what I will do, maybe I will keep them. Okay, anyway. So so here in the first case, your figure is simply going to be something like this, right? Okay, and in the second case, what does it tell you?
Center at C, 0. Center at C, 0 and radius is C.
So
passing through origin. So it's
you are-
passing through origin.
You are going to get something like this. Is it okay? Fine. And of course, it is going to depend upon whether that C you are taking as positive or negative. Is it okay? Fine. You may have a circle somewhere here also, right? You may have a circle somewhere here, isn't it? But in this case, your family of circles are going to be something like this, isn't it? Fine. Okay. Fine. So now, as maybe what I'll do. Okay. I'll just keep the differential equation. Fine. Basically, what I'd like to do is this, and this is this for the timeline. Let it be like that. Okay. So now, how to find out orthogonal trajectories? So, as you know, suppose this green one, they represent a certain, one parameter family of curves, and then suppose the pink one, they represent another one parameter family of curves in such a way that they are orthogonal to each other. So then what is going to happen? Like if you at this point you draw a tangent, and here also you draw a tangent, they are going to be perpendicular to each other. Okay. Then now let us assume that this green family of curves, it is represented by this differential equation. So that means if you take any point here, if you take this point to be a general point, xy, so then this slope of the tangent at this point, it is simply going to be given by dy dx, right? So if I call it, say, m1, so then m1 is going to be f of xy. Is it okay? Fine. Now, since this pink and green family of curves are perpendicular to each other, so this tangent must have a slope m2 in such a way that what must happen? m1 and m2, if you take their product, it must be -1. So that means m2 equal to your -1 by f of xy. Is it okay with everybody? Fine. Okay. So now, since I have already found out what is the expression for the derivative of the family of curve, derivative of the function which represents the family of curves for the pink one. So obviously, the pink one, it will be represented by this equal to -1 by f of xy. Okay. Fine. Or from here I can write down that minus dx dy equal to f of xy. So what does that tell you? That if I substitute in the differential equation of the green family of curves, like dy dx, because it is equal to f of xy, if I substitute f of xy equal to minus dx dy, so it is going to give me the orthogonal trajectories. Is it okay? Fine. So in your next, I'll come back to that later on. So this is the formal definition of orthogonal trajectory, and you can see on the right hand side, on the right panel to be precise, you can see how this has been worked out. Is it okay? Fine. Okay. So now let me come to this part. Let me come to this equation now, which of course you know that they represented a, one parameter family of curves, which were nothing but circles centered at the origin. Okay. So now, in order to find out the orthogonal trajectory of this, what we have to do, like orthogonal trajectories are given by, so it will be given by what? Minus dx dy equal to f of xy here. So that is minus x by y. Okay, so if you try to solve it, you are going to get dy by y equal to dx by x, and that is going to give you eventually y equal to cx. Okay, and you know that y equal to cx, they are nothing but straight lines with what property?
Passing through origin.
Passing through the origin, right? So simply you take whatever straight line you take passing through the origin, then you will see that they are going to meet those family of curves perpendicularly. Is it okay? Fine. So far so good. I hope this blackboard is not blackboard writing is not very clumsy. Fine. I have already given you the slides. Okay. Sometimes if I am very clumsy, just let me know so that I can be more cleaner. Okay. So maybe what I'm going to do, I'm going to get rid of this circle. Okay. I hope you have understood the concept. Let me get rid of this circle because I already have the figure there in the slide. And again, let me tell you one thing. Let me warn you about one thing. Like say, while describing the things in the blackboard, many a times, although I am speaking to you, I may not write that down in the blackboard. That doesn't mean that in your exams, you are also going to elude writing certain parts. No. As mathematicians, I want you to be precise. Okay. Please write down all the descriptions whenever you answer something. Okay. And I'm going to deduct points for that if you don't describe it properly. Okay, let me get rid of all this stuff. I'll just simply leave this behind. Okay, fine. So now let me come to the second problem. You already know that if I take the family of circles whose center lies on the x-axis, then this differential equation is given by this. This differential equation is given by this. So now, in order to find out the orthogonal trajectory of this, what you have to do, you have to simply replace dy dx by. So, or for that matter, your dy dx equal to 2xy x squared minus y squared. Fine. Okay, so far so good. So now see, whatever differential equations so far I have dealt with, I mean, they were extremely easy to work out, right? So here, I cannot, I mean, separate them out, separate the variables. Can you? Can you separate the variables here?
Yes, sir.
Yes. You can separate the variables here.
Yes. We can
X and
apply.
Y. Huh?
We
How?
can apply
Sir,
2xy dx minus
Huh?
y square plus y square dx is equal to
No. You are getting into something else. Will that exactly separate X and Y? That is my question. I want this to be something like phi 1x equal to phi 2y. Can you do that? My point is that.
No, it is
no.
Phi 1x dx. Homogeneous is there. So, like say, it is a little bit tricky, right? But as you know that because we are dealing with something like x squared plus y squared, and you know that this has come from the equation of the circle, right? So if we use polar coordinates, our life may become much easier. I mean, mathematically. Okay. So that is why just I'll give you one trick. You will see that that works wonder for many difficult equations. Okay. Fine. So now let us try to see how you can find out orthogonal trajectories for curves given in polar coordinates. Okay, so I'll just give you. Suppose this is x. This is not y. So, and suppose I have this is the curve, and suppose I am considering this point, which is r theta. So that means this length is your r. This angle is theta. Okay, and let me take a neighboring point. Let me take a neighboring point here. Say suppose this is P and this is this is Q. And let me draw a tangent here. Let me draw a tangent here. And let us assume that because this is the incremental, so let me assume that this is d theta. Okay, and then let me extend this line, and let us assume that the tangent makes an angle phi with this radial vector. Okay, fine. So now what I'm going to do, I am just going to draw a perpendicular at this point, perpendicular at this point. Okay, so that this angle is 90 minus psi. Is it okay with everybody? Fine. Okay. So now this is Q. This length is dr, and this length is r d theta. Do you agree? Do you have any doubt about the dr? Am I okay with that dr? Yes or no? Yes or no? Everybody is silent. It's fine because see what we are doing here. We are taking a neighboring point Q, which is very close to P, and so that means your d theta is going to tend to 0, right? So actually, if you have to consider these to be dr, so you should have a circular curve here in such a way that onto this tangent drawn to that circle, this radial vector is going to be perpendicular. But since we are simply approximating it, so this is correct. Okay, this is in the limiting sense. Is it okay? Fine. So now, if you want to find out the slope of the tangent, what we'll have to do, we'll have to find out tensile. And you can see that tensile is nothing but your cot 90 minus psi, and this is 90 minus psi. So the cot 90 minus psi is going to be your what? This base by hypotenuse. Okay, so it is going to be r d theta by dr. Is it okay with everybody? Fine. So as before, say if I call it as M1, as before, so if you want to find out the orthogonal trajectories of this curve, right? So then if you take the point of intersection of those trajectories with this one, then at that point of intersection, that tangent lines, they must be perpendicular to each other. So if the tangent to the orthogonal trajectory at that point has M2 as slope, so M1 and M2, if you take their product, it must be equal to -1. And for that, what you must have, M2 must be equal to -1 by r dr d theta. Okay, so what are you going to do in order to find out orthogonal trajectories in polar coordinates? So you are simply going to replace r dr d theta by -1 by r d r d theta dr by -1 by r dr d theta. That's it. Okay, fine. So that brings me back to this equation. So, but let us not try to backtrack from this equation by plugging in x equal to r cos theta and y equal to r sin theta. Let us try to work it out from the original equation. Okay. So now and if you have any question, you can simply unmute and just let me know. Okay, so now if you recall, my original equation was x squared plus y squared equal to 2cx. So if you convert it into polar coordinates, so this is going to be r squared, this is going to be 2c r cos theta. So this implies r equal to 2c cos theta, right? So this implies if you take your dr d theta, so this is going to give you what? Minus 2c sin theta. Okay, 2c sin theta. So this implies your r d theta dr. So this is going to be equal to what? What? Am I okay? Fine. Is it okay with everybody? What is happening?
Okay.
Okay. Sometimes I feel like the link has failed. Okay, fine. So in order to find out orthogonal trajectory, so suppose this is A. So therefore you write, say suppose this is B. Therefore the orthogonal trajectories of A is given by, and in your exam please don't write as simply OT. I want the whole orthogonal trajectory. Is given by simply replace it by what? -1 by r dr d theta, and that is equal to what? Your, am I doing it okay? Just a minute. R equal to 2c sin theta. Yeah, I should be fine. Minus r 2c sine theta. Okay, fine. So then can you solve it? Getting into something else. Just a minute. R dr d theta.
Sir, I think you have to eliminate the parameter.
Ah, good. I'm happy that you have roped it in. You have roped it in. So, like say, probably many of you would have gone in that way, right? So, how you find out the differential equation? So simply it becomes this. Then your dr d theta. This is equal to minus 2c sine theta. Then you eliminate the parameter because I would like to have r dr d theta dr. So I am simply going to write r by dr d theta, and that is going to give me minus cos theta by sine theta. Okay, and this is simply r d theta dr equal to minus cos theta by sine theta. Okay, see now I have gotten rid of the parameter c. So in fact, this is my differential equation which represents the circles like this which are centered at x. This is the differential equation of those circles. So in order to find out the orthogonal trajectories of this, what I am going to do, I am simply going to replace this by dr d theta. So cos theta by sine theta. And from here, eventually, you will see that it is straightforward. You are going to get something like r 2c sine theta. Okay, so that means you are eventually going to get r square equal to 2c r sine theta. That means x square plus y square equal to 2c y. Is it okay with everybody? Fine. This you can easily find out. This you can easily find out. Okay. So basically, what I mean to say is that this is eventually going to give you x squared plus y squared equal to 2cy. Okay. So which are nothing but what? Circles whose center lie on the y-axis. Okay. So now if I come back to this, then you will see that, like say, if you draw circle, I mean centered at y-axis, you are going to get something like this. You are going to get something like this. You are going to get something like this. Okay. So let me just show you. So from here, you can see that on the right panel, you have some dotted circles, which are nothing but the orthogonal trajectories to the solid circles. And you can see that the solid circles, I mean their centers, I mean light on x-axis, and here the center lies on the y-axis. Is it okay? Fine. So now let us try to do a. So this 5, I mean, have you done problems like this one before? Yeah. Can anybody tell me?
Sir.
You are familiar with this kind of problem? Problem number 5. See the, I mean, drawing part I'm going to do, don't worry about that. But have you come across any problems like that? Because there is some question being asked, like what conclusion can be drawn from this fact? So whether you have come across something like that, that conclusion which is going to be drawn, it is going to, I mean, expose you to something. So in fact, I'm looking for that something, whether you have come across that something before or not. It seems it doesn't ring a bell. Otherwise, somebody would have answered it very quickly. Okay, so now let me try to do this. So this is y square equal to 4c x plus c, right? And this is all parabolas which the x-axis as its axis and focus at the origin. And what you have to do, find out the differential equation of the. So
they are self-orthogonal.
Yes, they are self-orthogonal. So can you tell me what is the meaning of self-orthogonality?
Its orthogonal trajectory also looks like same.
Yeah, orthogonal trajectory and that curve family are same.
Huh?
Both are same. I think its name is oblique, that something like that. Oblique trajectories.
I'll come back to that same in a short while from now, and then I'll ask you. Okay, so if I want to draw it, what it is going to be like? They say that focus at the origin. Okay, so it is going to be something like this. Okay, if the focus is at the origin, so that means the vertex is going to be minus C0, right? Okay, and the directrix is going to be x equal to minus 2c. This is going to be my directrix. This is so basically this is x, this is y. So it is going to be something like this. Is it okay? So this is your just a minute. Am I okay? Y squared.
It's okay, sir.
It is okay, right? Y squared. Yeah. So this is y squared equal to 4c x plus c. Okay, fine. So now let me firstly try to find out the differential equation of this family of parabolas. So if I differentiate it with respect to x, so 2y dy dx, this is going to be 4c. Okay, so basically from here I am getting your c equal to y by 2 dy dx. Okay, so now simply eliminate c between these two. Now I can say that in order to eliminate c, I can simply substitute the value of c from this equation here. So that is going to give me, so maybe call it E or A. And rather than substituting, rather than writing the word substituting, I would prefer to use eliminating, no? Eliminating c between A and B. Okay, so that is going to give me y squared equal to 4 y by 2 dy dx, and then x plus y by 2 dy dx. So y squared equal to this is going to be 2y, so 2xy dy dx plus y squared dy dx whole square. Dy dx whole square. Okay, fine. So this is the equation of the this is the differential equation which represents this A, this one parameter family of parameters. Okay, so now as you know that in order to find out the orthogonal trajectories of this, I have to replace dy dx by minus dx dy. Okay, and eventually you will see that once you substitute that here, you are going to retain this equation. I'm leaving that as a homework. You can easily do that. Is it okay with everybody? Fine? See, you are still silent about this. I don't know why. And let me give you another homework. Instead of this, you can get a linear expression also by eliminating C. I'm telling you. You please try to work that out at home also. In Simon's book, they have given this as the answer. But I am going to take the other answer as well, the linear expression. That is also going to give you the same conclusion. Okay, fine. So now the orthogonal trajectories, in order to find out that what we will do, we will simply replace dy dx by minus this, and then y squared minus dx dy whole square. Okay, so now is it going to give you the same?
Sir.
You simply divide throughout by j.
Yes, this is the previous equation.
It is going to divide throughout by dy dx whole square. I think you are going to get this. Okay? Or yeah, if you divide it by, I mean, dx dy or dx dy whole square, so that means you are multiplying it by dy dx whole square, right? So simply you can multiply it by dy dx whole square. So this is going to become like say 1 dy dx is going to remain, right? And here it is going to be y squared. So once you transpose this to the right hand side, you get the same answer. Okay, fine. So now let us come to yeah, the answer to the last part is that what conclusion can be drawn from this fact that that means they're self-orthogonal. Okay. So if you want to find out the orthogonal trajectories of the given family of curves, you simply get a family of curves represented by same equations, but there is something here. So, like say, if I'm thinking about the same family of curves here, what is happening? Like say, I'll get something like again the focus being in at the origin. I'm going to get another curve or another family of curves where the focus is going to be at the origin. But from here, can you see whether the green curve and the white curve, are they orthogonal to each other? Yes? Are you getting my point, what I'm trying to say? See, from the eventual equation, like say this equation is nothing but this equation. Okay, we were trying to find out the orthogonal trajectories. Then we have seen that in order to find out the orthogonal trajectories, you get the same differential equation. So that means if I try to solve this equation, it is going to land me to something like this again. Right? So what is the mystery? Like say if I plug in this one, if I plug in or if I want to graph this, I'm going to get something like this, isn't it? And the way I have drawn them, it doesn't look like that they are orthogonal to each other. The green curve is not orthogonal to the white curve. So what could be the mystery here? Can you tell me?
So they are not interesting. Intersecting, sir. They are not intersecting, sir, I think so.
They are not intersecting. Okay, fine. Yes. In order to intersect, what must happen? Okay, I'll give you a hint. See, the directrix here, the directrix was your x equal to minus 2c. What kind of directrix is going to make it, perpendicular to each other? Are you getting the point? I think you are thinking too high. The answer is very simple.
Axis of parabola.
Huh?
Axis of parabola is perpendicular to the directrix.
No. It is not like that. See, basically what you have to do, the vertex, you have to shift it something like this. Is it okay? Okay, let me walk it out and then it will be clear to you. Okay, fine. See, why you are getting the same thing, let me try to explain it. See, suppose I am considering this one, 4c1 x plus c1, okay? And then let its orthogonal trajectory be given by 4c2 x plus c2. Okay, now let me see, what comes out of those C1 and C2. Then it will be clear to you what I'm trying to say. Okay, fine. So from these two, you can easily see that if I want to find out their point of intersection, right? So then okay. At point of intersection, what we must have? Like say, they must be equal, right? So then what is going to happen? C1 x plus C1 equal to C2 x plus C2. So this is going to give me x C1 minus C2 equal to minus C1 squared plus C2 squared. So this is going to give you your x equal to minus C1 plus C2, right? Is it okay with everybody? Fine? Okay. So now, if you plug in x equal to minus C1 plus C2 here, what you get from here? What you get from here? Yes? Simply, see, here minus C1 minus C2, right? So this C1 C1 goes, what we get? Y squared equal to minus 4 C1 C2. Is it okay?
If C1 or C2 is negative, then Y square is fine.
That is the mystery. That is the solution of that mystery. You are getting the point now. Okay, I'll tell you. So now, see, now you have seen that from here, what I get, that y squared equal to minus 4c1 c2, right? In order for that to be valid, what must have? C1 and C2 must be of opposite
sign, yes.
Right? Okay. And again, like I said, let me tell you that from these two relations, from this relation itself, I can get it. That these trajectories are orthogonal. See, suppose I am considering the first family of curves, like say y squared equal to 4c1 x plus c1. So from here, what I get, 2y dy dx. So this is equal to 4c1, right? So this implies dy dx equal to c1 by y. Fine? Okay. So let me call it for curve 1. So similarly, for curve 2, dy dx, curve 2, that is the orthogonal trajectories, you get C2 by y, right? Okay. So now they are nothing but the slope of the tangents, isn't it? At the point of intersection. So now if I multiply this dy dx 1 into dy dx 2, what I get? C1 C2 by y squared. Okay, just a minute. Here, not
2c1 by y.
Yeah. It is 2y, right? No, 2c1. Okay, so it is 4c1 c2 by y squared. And from here you can see that this is equal to -1. Is it okay? Is it okay? Fine. So they must be orthogonal to each other, isn't it? But they are going to intersect only when your C1 and C2 are of opposite sides. So that is only when what is going to happen now. So your vertex in this case, must be where? In the positive x-axis. Is it okay? Is it clear? The concept, is it clear? Why it is happening?
Yes, sir.
Yes, sir.
Why it is happening? Fine. Now I
Fine.
think it is clear to you. Okay. So this is the example of self-orthogonality. You please don't think that they are going to be of similar, nature. They are similar nature, but some conditions like this, it must have to be imposed for making them orthogonal to each other. Okay. So I think I will stop here. In my next class, I will start initial value problems. I'll start initial value problems, and then I'll start, Picard's theory of this one, uniqueness and existence. And in order to prove that theorem itself, probably we are going to take 2 or 2.5 days or something like that. So you have to bear with me. Okay, I hope it is not going to be boring. Okay, so then I will see you tomorrow at the same time, that is at 12. Okay, have a good day.
Excuse me, sir.
Yes.
Sir, I have class, sir, on tomorrow, sir, at 12 to 1, sir.
But that class has been rescheduled or what?
Sorry, sir.
No, that class was for which subject you have?
So differential geometry, sir.
That's an elective, right?
Yes, sir.
But the thing is that you have to then follow my recording. That is fine.
Okay, sir.
Okay. So my recording will be uploaded. Don't worry about it. You'll be able to follow from there. Okay. And if you have any doubt, just let me know.
Okay, sir.